It's not if someone asks about question 12 from 16D, it's when. This question has come up several times over the years. It's been around for a number of years, and I think it was even around when I was in year 12. So let's have a look at it. It's a corker, it's really, really tricky, and it's worth spending time trying to process how it works. The amount of a certain chemical type in a type A cell is normally distributed with a mean of 10 and a standard deviation of 1. Now, what does that actually mean? Right, a type A cell. So we've got this sort of type A cell. I don't know what a type A cell is, but I imagine this like a battery. All right, so I've grabbed a battery and I've looked at the battery, looked inside it, and I've measured the amount of chemical in it. And I've grabbed a whole bucket load of them. Okay, and what I notice is that when I measure it, the amount of a chemical inside it, whatever the chemical is normally distributed with a mean of 10 and a standard deviation of 1. What I can be 99.7% confident in, therefore, is that it's going to have between 7 and 13, plus or minus 3 standard deviations from the mean of that chemical. I can be 99% confident that that's how much stuff there will be in a type A cell. And I've actually drawn the distribution curve. I've used a software package to draw this for me. That's what it will look like. Here's the mean, which is 10, plus 3 standard deviations either side will be 99.7% of the values. All right, what we've also got is a type B cell, which is also normally distributed. So this is a different type of battery. So battery A and battery B. It's also normally distributed with a mean of 14 and a standard deviation of 2. So there's more variation in what we get with type B cells in terms of the chemical, because although it's got a mean of 14, it's got a spread or a standard deviation of 2. And that means I can be 99.7% confident that there's going to be between 8 to 20 of this particular chemical in a type B battery or battery B. Again, I don't know whether we're talking about batteries or something else, but it doesn't really matter. To determine whether a cell is type A or type B, the amount of chemical in the cell is measured. Okay, so we grab a battery and we measure up how much of this chemical there is. The cell is classified as type A if the amount in there is less than a specified value, C, whatever that value is, and type B otherwise. So if C equals 12, calculate the probability that a type A cell will be misclassified. And okay, let's just do the type A cell misclassification. So our benchmark is 12. So what we're looking for is the amount being 12. And in a type A cell, okay, and remember, I've just grabbed a battery, all right, and I'm looking at the battery and I've measured up how much stuff there is. I know that if the battery has 12, okay, so more than 12, it'll be type B, okay, or less than 12 will be type A, no matter what the battery is. Right, so if I've grabbed it, okay, and it's a type A battery, mind you, I don't really know that it's a type A battery, but I've grabbed it. If I measure less than 12 over here, okay, then I'm going to say that it is indeed type A. And that would be a correct classification if it is a type A battery. Now, if it's more than 12, what I'm going to do is classify type B. And that would be wrong, okay, for a type A battery. So if it's a type A battery and I measure more than 12, I'm going to go, oh, I've got a type B battery because my benchmark is more than 12, it's type B, less than 12, type A. All right, so what we want to know is the probability of misclassifying, i.e. the area under the curve between 12 and positive infinity. So we're going to use normal CDF or whatever it's called, distribution continuous norm CDF. Now our lower bound is 12. Our upper bound is going to be positive infinity. Our mean is 10 and our standard deviation is 1. Okay, so norm CDF 12 infinity 1 10 equals 0.02275 dot dot dot. Okay, so that is the chance of misclassifying a type A cell. All right, now we want to get the chance that a type B cell is misclassified. All right, so we've grabbed a type B cell, remembering that our benchmark or our number is 12. Okay, and if it's a type B cell, what I'm going to do is just grab it and measure the amount of this particular chemical in there. If it's less than 12, I'm going to go, oh, we've got a type A. Okay, even if it is a type B, remember I'm not looking at the label or something going, oh, energizer, obviously it's an energizer. Okay, I just know that I've got a battery in my hand. All right, so that's going to be a type A, and anything more than that will be type B. Now, if it is type B and I classify it type B, that's a correct classification. If I have a type B battery and I classify it type A, that is wrong. That is a misclassification. So this is what I'm interested in here, the probability that I'm going to classify it incorrectly. So I'm just going to manipulate my thing over here, and I'm going to get this area under the curve here, which will be from negative infinity all the way up to 12, with a standard deviation of 2 and a mean of 14. So that one's going to be norm CDF negative infinity 12 to 14 equals 0.158655 2 dot dot dot. Alrighty, let's have a look at part B. Find the value of C for which the two probabilities of misclassification are equal. I.e., what I want to get is the same area. I want the area under this curve to match the area under this curve. That's really difficult to do given that I've got two completely different distributions here. So this one here is a normal distribution with a mean of 10 and a variance of 1. This one here is also a normal distribution, with a mean of 14 and a variance of 4. So what I want to do is I want to grab both of these and convert them to the Z distribution. Okay, I want to get their Z scores. Okay, now I'm going to use this formula here. Z equals the actual take away the mean over the standard deviation. Okay, so it's written something like C take away mu over sigma, and that will give us our Z score. So what I'm going to do is do that for type A. All right, so here we go with type A. Now, what's the number that I've got? That's what I'm looking for. I'm looking for that value. That's the number C there. Okay, so what I'm going to do is work out its Z score. So Z equals C take away 10 over the standard deviation, which is 1. So that's type A. Type B is going to be Z equals also C, the magic number, C, the value that will make these two the same, take away 14 over 2. All right, now what I want to do is make these equal. So I want the probabilities to be equal. So I want the probability that Z is larger than, so I'm now looking at the Z distribution, larger than C take away 10 over 1. And I want that to be the same as the probability that Z is less than C take 14 over 2. All right, so what I'm basically doing is I'm saying on the Z distribution, I want the values larger than this particular Z score, okay, to be the same as the probability that the values on the standard normal distribution is less than this particular score, okay? All right, so that will then help us line it up. Now, here's the little trick, and this is the really hard thing to spot. So what I'm doing is looking for an area larger than this, okay, and this. Now, I'm going to rewrite this with something else here, Z less than. All right, now what I'm trying to do here, girls, is pair up the coefficients, okay, or use the same idea as equating coefficients. All right, so what I'm trying to do is match up Z less and Z less. At the moment it's Z greater than, and so I can't just equate these two off and say that they're the same as each other because I need everything else to look exactly the same. Excuse me. So now what I'm going to do is say it's Z less than. Now, what can I do here? I want this part here, which is the greater than part, okay? Now, instead of getting that particular Z score there, what I want to do is split that over to this side here and actually get the lower part, okay? So this Z score here, all I'll do is I'll just get the negative version of that one there. Now, why the negative version? So this particular Z score here will be, what's 12? That's 2 standard deviations above the mean. So that would be 12 take away 10 over 1, which is 2. If I wanted the negative Z score, which is this part here, what I could do is work this out, okay, and then negate it. And that will give me negative 2, which will drop me over to this side. So what this negative sign allows me to do is to move over and work out this area here instead of this area here. The benefit is now, if you have a look at what's happened, is I can line these up. This will be like that technique that we've used for equating coefficients. So what I can do is equate that with that, which is negative C take 10 equals C take 14 on 2. All right, that's negative C take, or plus 10 rather, equals C take 14 on 2. Let's multiply by 2. Negative 2C plus 20 equals C take 14. I've got negative 3C equals negative 34. And I've got C equals 34 on 3. So apparently what they're saying is that when C is equal to 34 on 3, what we're going to get is exactly the same chance of misclassification. Now let's try it out because I'm really curious. All right, so I'm going to put my 34 on 3 in here up to positive infinity. For this particular distribution, which has a standard deviation of 1 and a mean of 10. Now, what that's going to give me is the probability. What's 34 on 3? That's 3, 12s are 36. It's a bit less than that. It's like 11 point something. All right. So it's going to give me the probability from, what is it, 11 and 1/3. So here's 11 and 1/3. It's going to give me this area here. That's what it's going to give me now. Okay, so when I hit enter, it tells me that the probability is that. All right, and now what we're going to do is the same thing. So this is again proposing that if I go from 11 and 1/3, so this is, what's the scale? That's 11 and 1/3 would be roughly there. We're now after this area here. And what should happen is that area here should match the value we just got. So I'm going to go from negative infinity all the way up to 34 on 3 or 11 and 1/3 on this particular distribution, which has a standard deviation of 2 and a mean of 14. And let's hope that this comes out as exactly the same probability. If it doesn't, I'm in some strife. Banger. All right, so what that meant is that that particular value, 34 on 3, is the one that equates the probabilities, that will get the same probabilities. Now, again, why did I have to go through the rigmarole of Z? Well, again, it's really difficult to do it on two completely different distributions, okay? This has a different, they're both normally distributed, but they've both got different means and standard deviations. So what I do is I get down to the Z distribution, plonk them both on the Z distribution, and then go for it from there. And it makes it a hell of a lot easier to work out when we've got that, so much so that I don't even need a calculator to get the C value that equates them. A really well-crafted question, extremely difficult. Good luck with it.